Introduction. Students, today I am going to teach you three-dimensional geometry. Has anyone heard about it before?
Teacher, I have heard about the 3D glasses which we wear while watching 3D movies.
Yeah, you're right. You are probably familiar with two-dimensional Cartesian geometry by now. That is, planar geometry. With this, we will learn about three-dimensional space or solid geometry. Real-world objects exist in three dimensions. For example, a cuboid or a box is completely described by three parameters as follows: length, breadth, and height. Corresponding to that, each point in the Cartesian space has three coordinates: x, y, and z. Look at this figure carefully. The x-axis is along the length of the screen, the y-axis is along the height of the screen, and the z-axis will be the one coming out of the computer screen. Objectives. At the end of this lesson, you will be able to define coordinate axes and coordinate planes, explain coordinates of a point in space, find distance between 2 points and explain section formula. Coordinate axes and coordinate planes. Let us take an example of a bouncing ball in a room where one corner of the room is considered as the origin. We can take any corner of the room, for the matter any point of the room, as origin of reference, and relative to that the coordinates of the point change. Thus, the origin can be taken arbitrarily at any point of the room. Let us start with an arbitrary point O in space and draw three mutually perpendicular lines x-ox, y-oy, and z-oz through O. The point O is called the origin of the coordinate system, and the lines x-ox, y-oy, and z-oz are called the x-axis, the y-axis, and the z-axis respectively. The positive direction of the axis is indicated by arrows with thick lines. The plane determined by the x-axis and the y-axis is called xy plane, that is xoy plane, and similarly yz plane, that is yoz plane, and zx plane, that is zox plane can be determined. These three planes are called coordinate planes. The three coordinate planes divide the whole space into 8 parts called octants. Coordinates of a point in space. Let P be any point in space. Through P, draw perpendicular PL on xy plane meeting this plane at L. Through L, draw a line LA parallel to OY cutting OX in A. If we write OZ is equal to X, AL is equal to Y, and LP is equal to Z, then X, Y, Z are the coordinates of the point P. Again, if we complete a rectangular parallel piped through P with its three edges, OA, OB, and OC, meeting each other at O and OP as its main diagonal, then the lengths OA, OB, OC, that is X, Y, Z, are called the coordinates of the point P. The coordinates X, Y, and Z of any point are the perpendicular distances of P from the three rectangular coordinate planes YZ, ZX, and XY respectively. Thus, given a point P in space, to it corresponds a triplet X, Y, z called the coordinates of the point in space. Conversely, given a triplet x, y, z, there corresponds a point P in space whose coordinates are x, y, z. Example: name the octant where the given points lie. 2, 6, 8, -1, 2, 3. Solution: since all the coordinates are positive, therefore 2, 6, 8 lies in the octant OXYZ. Since x is negative and y and z are positive, therefore -1, 2, 3 lies in the octant OX-YZ. Distance between 2 points. We use the Pythagoras theorem to derive a formula for finding the distance between 2 points in 2 and 3-dimensional space. Let P is equal to x1, y1 and Q is equal to x2, y2 be 2 points on the Cartesian plane as shown in the figure. Then from the Pythagoras theorem, we find that the distance between P and Q is PQ is equal to square root of x2 minus x1 square plus y2 minus y1 square. In a similar way, it can be proved that if P is equal to x1, y1, z1 and Q is equal to x2, y2, z2 are 2 points in the 3-dimensional space, the distance between P and Q is PQ is equal to square root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. Example 1. Find the distance between the points 2, 5, -4 and 8, 2, -6. Solution: let P 2, 5, -4 and Q 8, 2, -6 be 2 given points. Therefore, PQ is equal to square root of 8 minus 2 square plus 2 minus 5 square plus -6 plus 4 square is equal to square root of 36 plus 9 plus 4 is equal to square root of 49 is equal to 7. Example 2. Show that the points -2, 3, 5, 1, 2, 3 and 7, 0, -1 are collinear. Solution: let points -2, 3, 5, 1, 2, 3 and 7, 0, -1 be denoted by P, Q and R respectively. The points are collinear if they lie on the same line. PQ is equal to square root of 1 plus 2 square plus 2 minus 3 square plus 3 minus 5 square. After calculating PQ, we get square root of 14. PR is equal to square root of 7 plus 2 square plus 0 minus 3 square plus -1 minus 5 square. After calculating PR, we get 3 into square root of 14. QR is equal to square root of 7 minus 1 square plus 0 minus 2 square plus -1 minus 3 square. After calculating QR, we get 2 into square root of 14. Here, PQ plus QR is equal to square root 14 plus 2 into square root 14 is equal to 3 into square root 14 is equal to PR. Hence, points -2, 3, 5, 1, 2, 3 and 7, 0, -1 are collinear. Section formula. Let the point R, X, Y, Z divide PQ in the ratio L:M internally. Let the coordinates of P be x1, y1, z1 and the coordinates of Q be x2, y2, z2. From the points P, R and Q, draw PL, RN and QM perpendiculars to the XY plane. Draw LA, NC and MB perpendiculars to OX. Now, AC is equal to OC minus OA is equal to X minus X1 and BC is equal to OB minus OC is equal to X2 minus X. Also, we have AC by BC is equal to LN by NM is equal to PR by RQ is equal to L by M. Therefore, X minus X1 by X2 minus X is equal to L by M. On solving, we get X is equal to LX2 plus MX1 divided by L plus M. Similarly, if we draw perpendiculars to OY and OZ respectively, we get Y is equal to LY2 plus MY1 divided by L plus M and Z is equal to LZ2 plus MZ1 divided by L plus M. Therefore, R is the point LX2 plus MX1 divided by L plus M. LY2 plus MY1 divided by L plus M. LZ2 plus MZ1 divided by L plus M. If lambda is equal to L by M, then the coordinates of the point R which divides PQ in the ratio lambda is to 1 are lambda x2 plus x1 divided by lambda plus 1, lambda y2 plus y1 divided by lambda plus 1, lambda z2 plus z1 divided by lambda plus 1, lambda plus 1 not equals to 0. It is clear that to every value of lambda, there corresponds a point of the line PQ, and to every point R on the line PQ, there corresponds some value of lambda. If lambda is positive, R lies on the line segment PQ, and if lambda is negative, R does not lie on the line segment PQ. In the second case, you may say that R divides the line segment PQ externally in the ratio lambda is to 1. Corollary. Corollary 1. The coordinates of the point dividing PQ externally in the ratio L is to M are LX2 minus MX1 divided by L minus M, LY2 minus MY1 divided by L minus M, LZ2 minus MZ1 divided by L minus M. Corollary 2. The coordinates of the midpoint of PQ are x1 plus x2 by 2, y1 plus y2 by 2, z1 plus z2 by 2. Example of section formula 1. Find the coordinates of the point which divides the line segment joining the points 2, -4, 3 and -4, 5, -6 in the ratio 2:1 internally. Solution. Let A 2, -4, 3, B -4, 5, -6 be the 2 points. Let P, X, Y, Z divides AB in the ratio 2:1. Therefore, X is equal to 2 into -4 plus 1 into 2 divided by 2 plus 1 is equal to -2. Y is equal to 2 into 5 plus 1 into -4 divided by 2 plus 1 is equal to 2, and Z is equal to 2 into -6 plus 1 into 3 divided by 2 plus 1 is equal to -3. Thus, the coordinates of P are -2, 2, -3. Example of section formula 2. Given that P 3, 2, -4, Q 5, 4, -6 and R 9, 8, -10 are collinear, find the ratio in which Q divides PR. Solution. Let point Q 5, 4, -6 divide the line segment joining points P 3, 2, -4 and R 9, 8, -10 in the ratio k:1. Therefore, by using section formula we get 5, 4, -6 is equal to k into 9 plus 3 by k plus 1, k into 8 plus 2 by k plus 1, k into -10 minus 4 by k plus 1. On solving for k, we get k is equal to 1 by 2. Thus, point Q divides PR in the ratio 1:2. Did you know? J. Bernoulli, in a letter of 1715 AD to Leibniz, introduced the 3 coordinate planes which we use today. L. Euler took up systematically the 3-dimensional coordinate geometry in Chapter 5 of the appendix to the 2nd volume of his Introduction to Geometry in 1748 AD. It was not until the middle of the 19th century that geometry was extended to more than 3 dimensions, the well-known application of which is in the space-time continuum of Einstein's theory of relativity. Summary. Let us summarize what we have learned. In 3 dimensions, the coordinate axes of a rectangular Cartesian coordinate system are 3 mutually perpendicular lines. The axes are called the x, y and z axes. The 3 planes determined by the pair of axes are the coordinate planes called xy, yz and zx planes. The 3 coordinate planes divide the space into 8 parts known as octants. The coordinates of a point P in 3-dimensional geometry is always written in the form of triplet like x, y, z.
Here, x, y and z are the distance from the yz, zx and xy planes. Any point on x-axis is of the form x, 0, 0. Any point on y-axis is of the form 0, y, 0. Any point on z-axis is of the form 0, 0, z. Distance between 2 points px1, y1, z1 and qx2, y2, z2 is given by the coordinates of the point are which divides the line segments joining 2 points Px1, y1, z1 and Q, x2, y2, z2 internally and externally in the ratio m:n are given by, and the coordinates of the midpoint of the line segment joining 2 points P, x1, y1, z1 and Q, x2, y2, z2 are.